Hi, AP Chemistry students. Mr. Lopriato here. So we are still looking at the basics of bonding, and so we're going to talk about the VSEPR theory and the VSEPR notation specifically in this video. All right, so we have seen Lewis structures. Here we have methane CH4, and the Lewis structures are good. They show us the number of bonding atoms, they show us lone pairs, they give us information about a molecule, but they don't do a good job of showing us the geometry. All right, if we look at the Lewis structure for CH4, it kind of looks like a cross or a plus sign. Whereas if we look at the ball and stick model of it, we can see it is that tetrahedral shape. All right, same thing with NH3. We can see that NH3 has that lone pair, but in this picture, it looks like a T shape, when in reality, it is actually trigonal pyramidal. All right, so and we can see in these ball and stick models, they don't show us the lone pairs. So these two different models, the Lewis dot structures and the ball and stick models, kind of need each other. All right, H2O. In this Lewis structure, it looks like a linear shape, but in reality, a water molecule has that bent molecular geometry. All right, so the VSEPR theory helps explain the molecular geometries. VSEPR stands for valence shell electron pair repulsion theory. Right, this idea that the electron pairs all are repelling each other, right? And those are those hybridized orbitals. And so it kind of looks like balloons, right? Because the hybridized orbitals look like balloons on their own. When we tie balloons together to a central atom, the balloons push each other out of the way and they naturally make these shapes: the linear shape, the trigonal planar, the tetrahedral, the trigonal bipyramidal, and the octahedral. All right. So when we use the VSEPR theory, we often see these big charts. And these charts have so much information in them, but we have to be able to interpret it to use it. So what I'm going to focus on is what's listed in the second column as the generic formula, right? That is the VSEPR notation, where A represents a central atom, X represents an atom bonded to A, and E represents a lone pair on that central atom. And we have in this chart, we have a note. There are lone pairs on X or other atoms, but we don't care. We are only interested in the electron densities or domains around atom A. So we have to define which atom is A. All right, so again, A represents our central atom. We get to pick which atom that is. X is the atomic substituent, right? Bonded atoms is what I usually refer to them as. And E is the lone pairs, all right? And if there are none, they will not be shown. All right, so CH4. If we designate C as the central atom, right, as A, well, each hydrogen is going to be an X. So it's going to have the form AX4, right? That should make sense. That is 4 electron domains. All right, if we look at NH3, if N is the central atom, we'll designate it A. Well, now the H is an X and the lone pair is an E. So it's AX3E. It is still 4 electron domains, but instead of X4, it's AX3E, right? If we look at this H2SO4 molecule, right, which is a little funky, we got double bonds, we got O's that are bonded to H's. If we set S as the central atom, we make it the A in our formula, in our X theory, AXE. Well, what's around it? 4 X's. It doesn't matter if it's a double bond versus a single bond, and it doesn't matter that there are hydrogens further bonded out to those oxygens. We are only looking at sulfur. Sulfur is immediately surrounded by 4 bonding atoms. And it doesn't matter how they're bonded, single, double, or triple bonded. It's just the fact that it's bonded to an atom. So AX4. All right, what if we look at oxygen? If we make oxygen the central atom, all right, it has 2 atoms that it's connected to, 2 X's, and it has 2 lone pairs, AX2, E2. All right. If we make this oxygen our central atom, the bottom one, now we have 1 atom that it's connected to, so X, and 2 lone pairs, AXE2. All right. So that's a total of 3 electron domains, right? So it kind of changes a little bit on us. All right. What if we were to look at just hydrogen? It's only connected to 1 other atom, doesn't have any lone pairs. Remember that duet rule. Its form, AX. That's it. All right, something like an expanded octet, PCl5. If we make phosphorus the central atom, we get AX5, right? We can go up to 6 in the number of electron domains. Here we have 5 electron domains. All right, what if we do it from the perspective of chlorine? If that top chlorine was my central atom, it would be AXE3, 1 bonding atom, 3 lone pairs. All right, something like ICl4 minus. If the iodine is my central atom, it is connected to 4 chlorines, so AX4, and it has 2 lone pairs on it, so E2, AX4E2, a total of 6 electron domains, 4 bonded atoms, 2 lone pairs. All right, so once we have this notation down, we can look at these charts and it'll tell us. Something like AX2 is going to be linear. Something like AX3 is going to be trigonal planar. Something like AX4 is going to be tetrahedral. All right, so these charts are really helpful. We can just look at exactly where we are on the chart, but only if we know the notation. All right, so we want to start with a Lewis formula or a Lewis structure, and from there, we want to convert it essentially into this AX form, AXE, central atom, bonded atoms, and the lone pairs.